Hey guys, welcome to the section 6.5 lesson on paired difference in means. On the previous two lessons, we've covered quite a bit of ground in chapter 6, looking first at proportions, inference for 1 and 2 samples, and then for means, 1 sample, and difference in independent samples. So let's sort of get our bearings here before we finish off this section with 6.5. So we had proportions. And then we have means, and then we've got a matrix here, which is 1 sample. So 1 sample, 2 sample. I don't know what that 2 was there. Let's try that again. 2 sample, that looks a bit better. So this was section 6.1, 6.3, and then that both of these, this is, remember, the matched pairs setup. So matched pairs can come up in proportions if you want to know which of a pair is greater, or whether you prefer candidate A or candidate B, or whether you did better on drug 1 or drug 2. Just kind of 2 observations on the same, but it ends up being a yes or no or A or B sort of response. Then for means, for 1 sample that was 6.2, for 2 samples 6.4, and so that's fine. But then when we throw in matched pairs, that's where we need to think pretty carefully, because we're going to have to be able to distinguish between the 2 sample and the matched pairs setup. I worked with the AP Stats program for quite a while. In some of the early tests, there was a lot of confusion and 1 or 2 classic problems on dealing with the difference between a 2 sample and a matched pairs. So that's why we start with design back in chapter 1. We need to be able to recognize what the situation is. And so we'll take a look at that, but be careful, study the reading, and there's a nice discussion in the interactive lecture on that I've assigned for you. So since I was doing the talking on Monday and Wednesday, I thought you would benefit from hearing kind of the publisher's approach to this. And so it does a nice review of, or I shouldn't say review, but connecting and distinguishing between the matched pairs and the independent samples. So make sure you work the exercises as you go. They're the mini quizzes, and then it asks you to use a stat key at one point to get a p-value, I believe. I'm suggesting you use the XPT function in R to get that p-value, and make sure that you remember how to use that. Now here's a link to a handout of slides that's essentially the same as what's used in the interactive lesson, so you can refer to that as a reference. That's the handout form. There's a little bit in RStudio Cloud I'll point to, and remember there's a file in there that talks about commands for dealing with means, and that encompasses the paired difference, but I'll also have a little bit of script to deal with examples for this section, and that's what I'm going to talk about shortly. So we're here, and then I'll have assignments posted for the warm-ups and hand-ins. Okay? All right, so let's take a look at these examples. You can click on that. I'm going to open up the handout that I have here. Okay, so we're looking at a paired difference in means. So the CAOS is a comprehensive assessment of outcomes in statistics. It's an assessment exam. It's an online multiple choice test on concepts covered in typical introductory statistics class like ours. Students take one version before the start of the course and another version after the course ends. Before and after scores for a possible random sample of 10 students are shown, and then I'll show you something comparable on R from the actual example. So we're interested in determining whether taking the course increases students' understanding as measured by this test. Why should we do a paired design rather than 2 separate groups? Well, we can see that in this case, what we've got are 2 observations on the same individual, right? Now, in addition to having 2 observations on each sub-student, and that makes the design setup to be a matched pairs. We might note that there's a great deal of a difference, a variation in the score, so there's a lot of heterogeneity between the individuals, so we benefit from pairing. We are interested in the increase in scores for individuals, so pairing the data is going to reduce the random variation. So now we're asked to find the differences for all 10 students, state the mean, standard deviation, and sample size for the differences here. So we just go ahead and calculate the differences. 17 plus 5 plus 7 plus 15. We hope most of the cases are going to be improvements. 23. 9 minus 3, 11 and 0. All right, you can double check those as I just did, and it looks to be fine. All right, now we've got these differences, and we want to get the mean, standard deviation, and sample size. So you can add those up and get the mean, but at this point, when I've talked about this example in the past, I sometimes get questions. I realize students have lost sight with R of how just to quickly get a calculation, because we don't have this particular data set easily available. We'll have a slight variation of it that I'll take a look at in a minute. But let's go over to RStudio Cloud. I've got this open, and I'm not going to worry about this yet. But let's just do library mosaic, so we have things like favstats available. And I use Control L to clear the screen in case you wondered how I did that. So let's see, gains, well, let's call it diffs, is scan of open close parenthesis. Now in that case, and I think I talked about this early in the term, but it was quite a while ago, this will prompt us, and we can just start pasting in data at this point, or typing data. It can have a comma in between or not. As long as it's numbers, it doesn't really matter. So 17, 5, 7, now it still wants more, 15, 25, 23, 9 minus 3, 11 and 0. But when we're all done, and we are all done, we hit enter one more time, and then it says fine, got what I need. So diffs contains the gains in scores. Now we could go ahead and do something like mean of diffs and get the mean that way. We could use favstats of diffs to get everything at one time. And that agrees. All right, so let's make use of the favstats. So we wanted the mean of 10.9. So let's record that over here. So X bar is 10.9, or X bar D, depending. But I'm fine calling this X bar, because what happens with a matched pairs is we reduce the data to a one sample situation, where we've just got a sample of differences, and then we're working with that and stating the appropriate null and alternative hypotheses. The standard deviation, S or SD, is given over here, and that was 9.2. And now remember, that can be positive or negative, so perhaps it's not so surprising, and there were some high and low values. So perhaps not so surprising that we have a rather large standard deviation. And then our sample size is 10, right? Sample size, so 10 differences. So test to see if the scores at the end of the course are higher on average than scores at the beginning of the course. Show all details. So we let mu sub d equal the average difference, or average gain, in scores. And our null hypothesis would just be what? That mu sub d is equal to 0, versus the alternative, mu sub d is higher on average, so greater than 0. The test statistic that we want to use is X bar minus mu, well, minus 0 in this case, over S over root n. Okay, so we can go ahead and calculate that. So we have 10.9 minus 0 over 9.2 divided by the square root of 10. And calculate that, and we get 10.9 over the quantity, 9.2 over the square root of 10. And we get 3.75. So that's quite an extreme value. Let's see, 3.75. Now our p-value, remember, so 3.75 is going to be way out here in the tail. And our degrees of freedom is 10 minus 1, or 9. This is on a t. Okay, so we're looking for that probability. It's a one-sided alternative. So our p-value is equal to the probability of getting a t greater than or equal to 3.75 and a t on 9 degrees of freedom. So that would be, let's see, I've got R open here. 1 minus xpt of 3.75, and degrees of freedom is equal to 10 minus 1. You could put 9 in there as well. So the 0.0023 is what we've got. Notice that it's so far out in the tail we can barely see the greenish showing there. So 0.0023. So that's our p-value. So we could fit our conclusion over here. We might say we reject H naught and conclude that we have strong evidence. So P is 0.0023. That students on average have higher scores at the end of the course than at the beginning. So we really are making inference about the difference in means, the difference in average scores at the end compared to the beginning, but we're doing it by looking at the average of the differences. And we're concluding that we have strong evidence that the scores have indeed increased. Now we have one last question, which is what is the average increase and compute a confidence interval? So we already got the estimate of that. So x bar is 10.9, so that's the average increase. But attaching the confidence interval, we're doing the statistic plus or minus the margin of error. So we have a t star value times the standard error. So we can flesh that out. That's the x bar plus or minus t star times s over root n, where these are referring to the differences. All right, make sure that we're making use of the differences when we compute those. Plus or minus, then the s over root n. We've seen once before, 9.2 over the square root of 10. What do we use for the t star value? Well, we go back to the t. Oops. Didn't want to do that just right. All right, let's go back, get my pen again. Don't use this a lot with Word, but it seems a little bit funky here. Let's see. All right, so we want the value that has 0.025, and well, we want the value that has 0.95 in the middle, so we want that t star value. And once again, we're talking about a t with 9 degrees of freedom. So let's go ahead and do that with the xct command. df equals 9. And so 2.262 is our right multiplier. So 2.262. And that's what we're putting in here. Too many twos here. 2.262, and then let's go ahead and calculate that. So 2.262 times 9.2 over the square root of 10 equals, so 6.58. Let me just double check. Yeah, why is that large, right? It's because our sample size is not very large, so 6.58. And here we get 10.9 plus or minus that. And then we go ahead and calculate the endpoints. Is 10.9 minus 6.58, so 4.32. We're still 4.32. We're still quite clear of 0, so it's consistent with our result above. 10.9 plus 6.58. Remember, so 17.48. So remember, when I say consistent, what I mean is that there's strong evidence of a gain, and so it's the interval is totally above 0. So once again, we want to interpret this, so we could say, let's make this red just so it stands out. So we are 95% confident that the average gain in CAOS exam scores is between 4.32 and 17.48. So that's the gain between the posts, so average gain in CAOS exam scores is between 4.32 and 17.48 points. Okay. And now this is, this was not an experiment in the sense that we're either not comparing we're not comparing the groups as two independent groups. We're estimating the size of the gain for the particular population that's represented by this sample. Okay. So when we say this, it's not that we're 95% confident that the gain for this group is between this interval. We know the average was 10.8. What we're talking about is the typical gain for students from whom we've sampled. So maybe this particular school with this particular instructor, or however we might want to frame it. But that's the inference that we're making. All right. Now, let's take this just a little bit further by going over to R and seeing how we could do the same thing, or at least most of the pieces here using R. So you'll find this in your Chapter 6 lesson. There's the link that I provided. I've called this R match pairs example. You'll be looking for the RMD file. Let's clean off that. I'm going to go ahead and open that up. And I'm going to make it bigger so we can see what we're doing. And this is useful because we can also work in line. Make it a little bit bigger. Okay, so the usual load mosaic, load the data. We want to make comparisons. So first inspect the format of the data. So whether you use the head command, you could use view, you could use glimpse is another one that I've sometimes suggest for just taking a look at what the data look like. That will give you a feel for it as well. So the main thing is that we've got an indicator variable and a pre and a post, but we do not yet have the differences. So it's going to be up to us to calculate the differences. Before we did it by hand, here in the next section, I've asked to find the differences and get the mean, standard deviation, and sample sizes. So I suggest using the mutate command that I've shown a few times before. Mutate the data set, gain equals, and just make a formula, post-test minus pre-test. We're creating a new variable called gain. To avoid confusion, I've put that in a new data set. So this new data set would have the pre, post, and gain, and it's called exam2. And we'll go ahead and get the summary statistics for that gain. And as before, we get the mean, the standard deviation. So the data set is not exactly the same as what we had over in the other example that we're just looking at. Let's just take a quick look at those gains. What do we want to do? Maybe we can use glimpse again for the new version and see that it's showing up. All right, so here are the gains, 17.55, 17.5. We can compare that to what we're dealing with over here. So 17.5, 7, 15, 5. Yeah, here was 5, 25, 15, 17. So some large differences. So it's definitely different. At first they're similar, but there are a few differences. There's a gain from 37.5 to 55. So just to confirm, we didn't really expect the means and standard deviations to be the same. This is the built-in data set. So it's to give another data set to look at compared with what's in the example. But same syntax, or same basic commands that we would use for the ones in the example we just looked at. I wanted to give you an example of a dot plot, how to sort of check for the conditions that the data are normal. So I'm plotting just the gains. No need really to plot the before and after separately. What we're interested in is the gains. I adjusted the figure size. You'll see on the final when I knit it that it's more compressed, so I set the height to be 1.5. That's kind of a relative number. It's not really inches, although kind of maybe it is. I don't worry too much about. Sometimes you're using points, sort of in the typesetting sense, but 1.5 is going to be pretty narrow or pretty small plot, not very tall plot. Dot size 0.25, so if we run that, we'll see that it's squished and we're not worried about the counts, but we just see where the points are. And, nothing super obvious in terms of real big outliers. So that's about what normal looks like when you have a sample of just 10. It's not going to look like a smooth bell curve. All right, test to see if the scores at the end are higher. So we're going to reduce it to a one sample test. We're just looking at the gains. By default, the null hypothesis is set to be 0. An alternative is greater. Otherwise, if it was something other than 0, we'd specify the mu, as we saw before in the one sample case. T is 7 now. Degrees of freedom is 9. P-value is super small. And our alternative hypothesis is that the true mean is greater than 0. Or sorry, yeah, that was a one-sided alternative. So we have very strong evidence against the null in favor of the alternative. If we compute and interpret a 95% confidence interval for the gain, we get this. We get an average gain of 9.44 to 18.556. Now remember, all right, so that shows the commands that we would use. Now let's see, what did we have? We had diffs in here. So just in case you're wondering, let's once again do favstats of diffs. I have misspelled it. Okay, so remember we had a mean of 10.9, standard deviation of 9.2. If we'd done t-test on that, we don't need a data frame name here because we didn't put it in a data frame. We do get the 3.7 and the p-value of 0.005. Well, that looks a little funny actually to me, and I think I've got something I need to fix here. If we go back up here, I had the digits set pretty small, so I'm going to change that to something more like 8 and run that. And then I'm going to run all the chunks, including these. And so we'll get really more digits than we need here, but I wanted to do some overkill just to note that this is here. And then let's see if I can go ahead and rerun the t-test. The favstats, sorry, let me clean this up for you. It's okay. Behind the scenes here. So favstats of diffs again. So we get the full detail here, but then the t-test of diffs. Okay, I don't need it there. So the 3.7, 4.0026, remember we need alternative equals greater. I think I had forgotten that, but what got my attention was the rounding of the 3.7 to just one decimal place up above. So I knew I had the digit set too small. So sorry about that. So the one-sided alternative 0.0023 does indeed agree to what we had found over here. The 3.75 lines up, subject to rounding error. And then if we wanted the confidence interval that we got, we could do it like this, and $conf.int. and then we get 4.3 to 17.49, and that lines up with what we had over here. Okay, so yeah, I just wanted to fix that up so that you could see the correspondence first with what the specific numbers that we'd use here, and then with the built-in data frame called CAOS exam, whose numbers are not the same as on the example sheet. Okay, so you've kind of seen two examples with different sets of data. Okay, enough on that. Good luck on the problems and the warm-ups and the hand-ins, and let me know if you're running any problems, and have a great weekend. Take care.